So we had yesterday night. Was everybody here? I think everybody was here. Weren't they yesterday? Okay, so that's good. So the key thing is basically the types of questions that will come from these Theorem 3 type problems will be just the mechanics of doing the calculations. Okay, which would be you either have to figure out how many rectangles or trapezoids would be necessary to be within a certain max error, or find out what the max error is for a certain number of trapezoids or rectangles or so forth, right? I mean, those are the mechanics of doing it. So we want to make sure we can do that. And of course, in either of those cases, you have to find this K1 value or this K2 value. We got to be able to do that with our calculator. So go ahead and get your calculators out now. Would be a good thing. Who wants me to present? You got blood drawn already. How'd it go? Did you pass it out?
No.
Okay, thanks, Cody. All right. So is that the first time, Claire? Or have you done it before?
I done it before.
Okay, log in. All right, so any questions on the homework? I have a couple in mind that I might want to talk about a little bit, but we'll see if anybody else has something they want to talk about. Because the other thing we have to be able to do besides the mechanics of it is we need to be able to understand what this is doing and be able to answer some questions about that. And there were several of those kind of questions in here as well. Hi, Cody. All right, so nothing, easy, no problems, move on. 1B, okay. I got 1A, but I need 1B. Yeah. So yeah, what's it say?
So it says let the integral sine x squared from 0 to 3 x.
Oh, right. And then you're talking about in B.
Yeah, B.
Okay.
Explain why I is between 0 to 7, 5, 4, 7.
Okay. Yeah. So exactly. That's exactly the kind of thing I'm talking about. So if it says I minus M50, and then it says show that I is between 0.754 and 0.795. Okay. Now they wanted you to go ahead and use Theorem 3. So you had no problem with part A, right? Theorem 3, M50. It came out with less than or equal to 0.02, it says. Okay, so fine. We'll trust them on that. That's what it was. All right, here's what it would be. And this is where you would, now I may not ask it just like this, but here's where you would get on your calculator and use that area program. So let's do that. That's what you would do. Because what you're going to need here is you're going to need to know what M50 gave you. Okay, so let's go to our calculator program. Okay, and let's do sine of x squared. And so we're going to go to our calculator because we need to do M50. And so, of course, that's way too many to do by hand. And so we're going to go from 0 to 3. 0 to 3, I think it says. And we're going to do 50 subdivisions. And our midpoint is 0.77, what is it, 0.774? 385, is that what it was? Okay, all right. So that is our midpoint. So now think about what that means. We don't know the exact area, because sine of x squared, so this is a really, I'm glad you asked this question, because this is simple, it's supposed, number one, it should be easy, right? No. This really gets at one of the things I'm talking about here of understanding what's going on so you can be able to answer these questions they're asking in a different way. So we know this isn't exact, right? I mean, forget all the other things that the area program showed us. We know this is 50 midpoints. It's probably under, it's probably over, but we really have no idea how far off it is. Oh, enter Theorem 3. Theorem 3 has told us that the most it's off is 0.02, right? That's what Theorem 3 says. That's max error. So that the most it's off is 0.02. So what could we do to get a range of numbers? We could add 0.02 on, right? So maybe this is under by 0.02. So add 0.02 on, what do you get? 0.79, 794 actually, okay, but close enough. Or we could take off 0.02, and that would be 0.754. And that tells us that the exact answer, we don't know what the exact answer is, but because of Theorem 3, we know that the most it can be off. The most, and so when I say the most it can be off, I'm talking about the approximation. The most M50 can be off is 0.02. So add 0.02 onto it, take away 0.02, and that is going to give you exactly or not exactly, that's going to give you the bound, the range that you know the exact answer's got to be in. Make sense? That's how you show it. You just add or subtract 0.02. Okay? That is also, well, I'm not sure that came up in another one. There was one that talked about computational error, but we'll get to that one in a bit. I want to talk about that one. Yes, thank you. I did remember, yeah. Okay, thanks. Okay. All right, anything else? Good question. All right, let's talk about a couple here that I want to make sure we're up to speed. So Cody, do this one for me. This is number 9, and I want to do part C. I want to talk about part C here. So part C talks about midpoint. I want to talk about C and D. So, and let's just do the midpoint one on C. So, go ahead and do our second derivative, Cody. Get the second derivative for us and graph that thing. Okay, so a midpoint, we're going to do M3. So that's going to be our K2 value, which we're going to get in a minute. Okay, let me move this over so you got small. Okay, so let's talk about a little bit of number 9 here. So we're going to need K2 right here. So he's going to do the second derivative for us. 4 minus 1 cubed, and then it's 24 times 3 squared. So that would be our max error for this one. Now, looking at number C, letter C here. Now, it does say compute exactly. I better do part A. So now, if I ask you this on the quiz, you need to understand fundamental theorem means show your work. Now, if you have the calculators, you could let the calculator give you the antiderivative. This would be x to the negative 1/2. So when we raise that up 1, that'd be x to the 1/2, divide by 1/2. So it'd be 2x to the 1/2 from 1 to 4. Put in a 4, square root of that is 2 times 2 is 4. Put in a 1, square root of that is 1 times 2 is 2. So the exact answer here is 2. So we know the exact area is 2. So sometimes we do that. We do a problem where we know the exact area just so we can compare. Okay? So now, let's catch up with Cody here. So if anybody has any questions, right? Second derivative, we're doing a midpoint, so that means K2, which is second derivative. We do the second derivative. Now we're going to go graph that thing. So he's going to copy and paste it. Into the graph screen. Okay, he's going to copy. Let's go to the graph screen. And let's, we'll get rid of that one. Now, do me a favor, don't put the absolute value on this one. Somebody in the other class, right? How many people put the absolute value on when they graphed? How many people didn't put the absolute? Okay, so it's 6 1 half does the other. Now, now we need to do a zoom fit, so let's do a 1 to 4. Okay. Because we worked, I think somebody in the other class asked about number 11, maybe it was, and that one was negative, right? And the max was way down in the negative, so that's fine. Just trace to there, it's actually the minimum, but then you use that value. Remember we talked about that yesterday. If you get an F prime graph, because I might give you just an F prime graph and ask you, what's the K1 value, right? Well, if it went up to 2 and down to -3, what would be your K1 value? +3, right? Just so you understand that, we're looking for that biggest number, regardless whether it's positive or negative. That's why we could put the absolute value bars around it. But anyway, these are all positive, so it's not a big deal. Well, clearly the max is where? Back at 1. So go ahead and hit a 1, trace, and hit a 1 here, and get us our K2 value. And this one actually is exact, 0.75. You can tell because it doesn't keep going. That's actually exact. 0.75. So go ahead and use that. You don't have to bump it up. But remember, and here I still have one on the screen here, or on the board. So if you got, yesterday we had 2.28537, whatever. So if you want to go to the 5, bump it up to a 6, right? Don't just type in whatever number's on your screen. You always got to bump it up 1 decimal. We want the worst case scenario. Now, somebody in the other class asked this, which was a really good question. They said, well, if your K2 value is just supposed to be the number, if it's not the exact max, if it just has to be a number bigger than the max, couldn't you use 10? For this one, 0.75, couldn't we use 10? Why wouldn't we though? Well, yeah, the max error is not as useful then, right? The max error is not as useful because remember what we find out here. What we find out here is what's the most it can be off, right? Now, or how many rectangles do we need to get 2-digit accuracy? Well, maybe it's 1,000 rectangles. Well, maybe we don't even need 1,000. Maybe that gives us 5-digit accuracy, but that's not the point. The point is we want a guarantee. We want a guarantee of what the max error is. We want to know if I do this many rectangles, I guarantee those first 2 digits are accurate. Now, maybe the next couple after that are accurate, but who cares? That's not the point. How much accuracy do we want? This guarantees that we'll get it. So we want it to be a useful error bound. So you don't want to just use a 4 here or a 6, right? Even though technically that'd be okay, it would make your computation, it'd make you have to do way more rectangles than you needed. So you want to get a useful error bound, but you still want it to be the max. Like Harish, I think, said, well, could we average? Could we take this high point and the low point, kind of average it? I said, yeah, but the problem is that would give you less rectangles to do, but you wouldn't be guaranteed then that it would be within a certain accuracy. That's the key. So that's why we do the worst case scenario. Okay, so now we're going to do 0.75 here. So we come back to this problem, and we're going to put a 0.75 in here. So go ahead, Cody, and do that calculation right there. Well, now you got to be careful. If you do it like that right there, if you don't put parentheses around that 9 and 24, you're going to be in trouble. That's where doing that fraction button can be nice, that control in the fraction. But yeah, it's got to be that. So 0.09375. Okay, so we get so we get 0.09375. Now that's our max error, that 3 midpoints. That's the most that 3 midpoints will be off. All right, now let's read what they've asked here because this is important you understand all this. So B says, compute the actual approximation error committed by M3. How do we do that? What else do we need up here to be able to compute the actual computational error? We actually have to do M3, right? So let's do that because that's good practice because that is going to be on the quiz, right? You have to be able to do M3. So you could do 4 minus 1 over 3, right? And then you could do, now we probably need a little number line here. So this is 1, this is 4, and you're gonna do 3, so that's easy, they're gonna be 1 wide, but where are the midpoints? The midpoints are in here, right? So 1.5, 2.5, 3.5, so f of 1.5 plus f of 2.5 plus f of 3.5. Okay? So there's your midpoint. Now, if on the quiz you'd rather do our old way of doing midpoint, you'd go f of 1.5 times 1, and f of 2.5 times 1, and f of 3.5 times 1, right? If you want to do that, height times width, whatever, that's fine. But remember, if it's single digits, you've got to write it out, okay? So you write out your M3, however you do it, and that comes out to be, why don't do that for us, okay, yeah, 1 over square root of 1.5, 2.5, okay, then add those up. .98347. Okay, so 1.98347. Now it turns out that we actually know the answer is 2. So the actual computational error is this right here, right? And so that's going to be those two subtracted. So go ahead and subtract those for us. 0.01 what?
6525.
Okay, round that. So now look at this. That's how much we were actually off. This is how much the theorem said we were going to be off. Right now, it's not how much we were going to be off, but that's the most we could be off, right? The most we were going to be off is 0.09375. Turns out we were actually off this. Now, that's like 9 times as much, or at least 7 times as much, right? This is like 7 times as much as this. So it's really not, this is really not good at saying how much you'll be off, right? It's important you understand that. That's the most you can be off. Turns out we weren't off nearly that much. Now, actually, you can go back to your graph, Cody. Go back to your graph. We can tell why is that? Why was our max error so much more than what we actually were off? Because we assumed that this graph was going to have a curviness, right? This is second derivative of 0.75 the whole time, when in reality it doesn't have that curviness hardly any of the time. Just up here, most of the time, the y values are way down here at like 0.1 and 0.2. So it has way less curviness, which means the midpoints are going to be way more accurate than what we're saying here, right? If this graph would have been fairly flat up here and around 0.75 most of the time, then our max error would have been pretty close to our actual error. Does that make sense? Okay, but since we're using 0.75 as our curviness factor, that's what K2 is, and it's really not that high most of the time, our max error is not as useful. But that's okay. That's okay. We don't care about that as much. We want it to be as useful as we can, and that's as useful as we can get it on this go-round. Okay, the last part of 9 then says, is this consistent with the error? Yeah, it's consistent. It said the most we'd be off is this. And we were off less than that, so that makes sense. Okay, then the last one says, what would you need to be within 0.005? So let's just so we review that for everybody. Let's go ahead and do that. So we had 0.75. So Cody, let's go ahead and solve this one. So we'd have this. We'd have 24n squared less than or equal to 0.005, and then we just get on our calculator and we solve that thing. So we're going to solve that. It was 4 minus 1, or just 3 cubed. And then over 24n squared. Nope, n. We don't know what n is this time. Right? We're solving for n this time. So we've got n squared. And then less than or equal to 0.005. And then comma n. Okay, so we ignore the negative one. So we need 13. So we're going to need 13. We would need, this is saying n is going to have to be greater than or equal to 13. We're going to need 13 midpoint rectangles to get within 0.05. Okay, guaranteed. Now we're probably going to be closer than that, but that will do it. Remember, 3 midpoints almost got us there. It was like 0.01 off, 0.016. So probably 6 or 7 midpoints probably will do it. But that's okay. We don't care. We want to know how many will guarantee that we get that. Okay, I want to talk just a little bit about number 27. Okay, number 27 is this one. So Cody, go ahead and do the derivative of this right here, of cosine 1 over x. So I've already done a little bit on 27. I don't know why nobody asked about this one, and maybe I don't know, but maybe you got this all figured out. But this relates to something we just talked about a minute ago, or two. Okay, so I went ahead and just did the actual area on the calculator. Now it's an approximation. The calculator's doing an approximation, but remember, it's set. So these are actually accurate digits because the calculator's set to do that using very much the same thing we're talking about here. Okay, so according to our formula, we're going to need K1 here, which we'll find in a minute. We'll have 11 minus 1 squared, and then we'll have 2n, and we're going to see how many, and we want that to be within 0.05. So we're going to solve that in a minute. So let's go to our graph screen. Okay, so he's done the derivative, so let's go ahead and graph that. And we're going to do it from 1 to 11. Okay, we're pretty close there, but we got to change our window just a little bit. Okay, zoom fit it. Okay, now see, this is very much like the one we were just doing, right? So go ahead and trace it 1. Because that's clearly where the max is. Okay, so we're going to go 0.842. 0.842. Now this is first derivative, so this is slope. So this is going to assume our slope is 0.842 the whole time. But what's happening? But the slope isn't 0.842 the whole time, right? Most of the time, it's way down here, like 0.1 something, which means it's pretty flat. And what happens to left rectangles when the graph is pretty flat? They're a good fit. They're a good fit, which means there's probably not much error. But if the slope is 0.8, 45 degrees almost, they're not a very good fit. If we assume it's 0.842 the whole time, again, it'll guarantee us. So here's the point of this problem. So if we go ahead and use 0.842, now the back of the book used 0.8415, so let's do that. Is that reasonable? Is that rounded up? Go back to your graph. Go back to your graph real quick. Yeah, 0.8415. Okay, so go ahead. Go back to your, let's use that. And then 11 minus 1 squared. And then, what would it be? 2, n. Is it just 2n? 2n on the bottom. And then is less than or equal to, we got to do a solve. We got to put solve for this. Just type it, S. Otherwise, you're going to get in trouble with your parentheses. Maybe that would have been faster. Left parentheses. There you go. Okay. Now we're good. And then less than or equal to 0.005, comma n. Okay, 8,415 left rectangles is what this is going to take, because that was such an over approximation of what's going on. So 8,415 left rectangles are going to be needed. So then they say, how about if we do this? Okay, how about if we say, let's take that 0.005, let's take that error that we want to be within, and let's split it up. Most of the error is going to be in the beginning of the problem where it was steeper. So let's put 0.004 of that error. This is what they told you to do in part B then. And C, let's put most of the error in the first half, 1 to 6, and let's put the rest of the error in that half, and then let's see how many rectangles are needed. Well, that would be then your 0.8415. That would be 6 minus 1, so you can go ahead and calculate this here, Cody. And we're going to do that calculation there. And then the rest of it, then we're going to have to figure out our K1 there. And then we'll go here. And let's see how many rectangles are needed there. Okay? And so we'll go ahead and do that first calculation. So that's 0.004. Now that we've cut that area in half, see, now we only need 2630. Now we only need 2,630 rectangles for the first part, and now we need a K value here, so we better trace. Let's go back to your graph and let's trace at 6. It's going to be at 6, right? The max is going to be from 6 to 11. The max will be at 6. Look at that. Look how small that slope is. Pretty flat. So these left rectangles are going to be pretty good. Okay. So what was that? 0.0047. Yeah, let's go 0.0047. So we're going to go 0.0047 on this problem, and we're going to see what, and our amount of error is even just 0.01. And so we go ahead and do that. Look at that, only 59. Only for that whole time. We only need 59 left rectangles to be within 0.01. Because that graph's so flat, the slope is the big slope was 0.047, so it's basically flat. So hardly any error. So look at that, add those two together, and so you get less than 2,700, 89? 2689 rectangles would be okay if we divided that up a little bit instead of 8,415. Okay, so that, but again, all that does is just give you this idea of, how we're figuring the max error, what that K1 and K2 value represent. K2 is like the max curviness, K1 is the max slope, max steepness, which causes our error. Okay, so be able to use the formulas for sure. Those questions will be on there. But there could be some question about, this kind of stuff as well. All right, let's get your notes out so we can get through what we have to do today and hopefully leave you a little bit of time to work on some things. You're gonna still be up here, Cody. So everybody needs their calculators out if you haven't had your calculator here, because there is going to be a calculator component to this as well that we'll be using on the quiz. All right, so this is going to seem at the start very unrelated to what we've been doing, okay, so far. I mean, it doesn't have anything to do with rectangles, it doesn't have anything to do with area, it doesn't have anything to do with intervals, okay? So why are we doing this now? Well, you're going to see real shortly here the connections to what we're doing and why we're investigating this right now. Okay, this gentleman's name was Euler, is how that's pronounced. Euler, not Euler. Okay, Euler. Okay, Euler's method. What Euler's method is a method for numerically solving differential equations. Okay, so now let's review what a differential equation is. What is it? An equation with a derivative in it. Now, a few quizzes ago, we had a question, what's a differential equation? People were writing things like it's an equation where the derivative exists. No. People put it smooth. No, that's differentiable. Okay, that's not a differential equation. A differential equation that has derivatives in it, a y prime, a p prime, a y double prime, something like that. That's a differential equation. What's the solution to a differential equation? The original equation. So if you have p primes in it, then the p equals is your solution. If it's y primes in it, the y equals is your solution. What's an initial value problem? What do we add in to get an initial value problem? An initial value, an initial condition. If we give an initial, because, for example, right up here on the board, here's a differential equation we're going to work with today. Y prime equals 2x. The solution to that is y equals x squared plus c. We do the antiderivative. Now, you can't always do that on problems. What if this would have been y prime equals 2y? Then we can't do that. Okay? If I give you an initial condition, that's called an initial value problem. We plug in the initial value, and it allows us to find the c. Okay? All right. That's differential equations. Now, solving differential equations means find the original function. Sometimes you can't do that. Now, sometimes you can with a straight antiderivative, but sometimes you can't. or we haven't learned enough yet to do it. So how can we solve it? Well, we did slope fields. Slope fields were when we plugged in numbers and we made those little slope segments. Remember that? And then we fit the curve. We just went with the flow and we wrote the curve in there. That was the original curve. That was the Y curve. Now that was very rough. That was a very rough estimate of the solution. So what Euler's method is going to be is a numerical way of estimating the solution. So right there is a connection to what we've been doing. We're estimating, we're approximating the solution. Well, that's what we were doing with areas. So there's a connection right there. All right. So I don't know that you need to write the rest of this down. This is just review. So slope fields were a graphical method for solving differential equations. What we're going to do here is a numerical method for solving differential equations. And here were just a couple of examples of some differential equations, okay? Now, you don't need to write this down. Just to remind you, so the way we were doing slope fields is we would come in here and we would plug numbers in here for our slope. So if I put a 0 in here for y, we'd get y prime is 0. So right here, whenever y is 0, right, whenever I put a 0 in for y, which would be all these points, the slope is 0. If I put a 1 in right here, we get y prime is 3. So every time y is 1, we'd have a slope of 3. Like this, right? If I put a negative 1 in here, y prime would be negative 3. So down here, the slope would be negative 3. Remember that? And then what if I give you an initial condition? What if I tell you y of 0 is 1? Well, you would know it goes through there. So you would kind of draw this in and you'd say, okay, it's kind of going like that. And actually, it should surprise us because this is actually one that we were supposed to memorize. Remember y equals AE to the KT? Remember that? Y prime equals K times Y it's an exponential. So it actually shouldn't surprise us that we have this. Now, here's our goal today. Our goal today is to say, okay, if y of 0 equals 1, what's y of 2? What's y of 2? Well, I could keep going with my graph, right? How much confidence would you have in the quality of that point right there, right? It's a pretty rough estimate, right? So we're going to come up with a numerical way to get a better answer for that. Okay, so here's what we're going to do today. We're going to do this problem right here. Now, here's another connection to what we've been doing. So you can write this down. Y prime equals 2x, and y of 0 equals 1. Y prime equals 2x, and y of 0 equals 1. That's our initial condition. Now, I've already solved it for you on the board here. Okay? Now, you don't have to write this other part down, the 4 steps, the 10 steps. You don't have to write that part down yet. Okay? Well, you can write the 4 steps. You can do that if you want. You can write that down. Now, we already know the answer, and what we're going to try to do is find y of 2. Right? We're going to try to find y of 2. Now, we're not going to solve for the whole y curve, the whole y equation, but we're just going to find y of 2. Okay? Now, I've already done it here. I've already done it up here. I did the antiderivative, put in a 0, 1, found the c to be 1, and so we know y of 2 is going to be 5. Right? We know y of 2 should be 5. Okay? But remember, just like we did with areas, sometimes we do a problem where we know the exact answer and then we do the approximations anyway. But we're learning things about what's going to happen when we don't know the answer. Okay, and we do the approximations. Okay, so we know the answer is supposed to be 5. Okay, so we're going to use 4 steps and we're going to use 10 steps. The rules are going to be the same. If it's single digits, you have to write it out by hand. So there's another connection to what we were doing. If it's single digits, you have to write it out by hand. If it's double digits, we're going to use our calculator. Now, it's not a program. It's not that same program as before. That was for area. But we're going to trace on our calculator. You're going to see here in a minute. Okay? All right. So, let's do the one where we do it by hand. So, we're going to do 4 steps to find y of 2. Now, let's think about that for a second. You can write this down if you want. We're going to go from 0 to 2. Right? We're going to go from 0 to 2. We're starting at 0 because that's what they told us. That was the initial value they told us is that x equals 0. Now, we're going to want to go to 2. Now, we're going to want to do that in 4 steps. So, if we're going to do that in 4 steps, how wide is each step going to be? Does that sound familiar? How do we calculate that? That looks really familiar, doesn't it? That's our old delta x, right? It's the same thing. Now, we're actually going to give that a different name when we're doing these problems. We're going to call that our step size. We're going to call that our step size. But it's the same thing. it's the same thing as the width of our rectangles, the width of our trapezoid. So we're going to call that our step size. So that's going to be how much? 1/2, and we're going to actually probably use decimals here. So our step size is going to be 1/2. Okay, so now I've got a little PowerPoint here to go through with you that will do this. This, by the way, is Euler. That's a picture of it, I guess. I don't know, it was a long time ago, 1700s. Swiss mathematician. Here's another picture of it. These are things in math that he's given credit for either originating or making popular through his initial mathematical work. That's quite a list right there, right? Different things that he's credited with. All right, so here's what we're going to do. So you're going to to do 4 steps. So what do I mean when it's single digits? You have to do the work. You have to work it out by hand. Here's what I mean. Okay. So here's an easy one. So we've already written all this down. dy dx same as y prime. Okay. So here's what we're going to do. All right. We're going to you don't have to draw the graph, but that'll be nice for us to look at. This is a graph of y over here. Okay. So we're going to make a table. So when I say do Euler's method by hand, I mean make this table. Okay, it's a little bit like Newton's method, not quite as long. Now, don't do the end column. I'm going to leave it. You can. I don't care. That's just counting the number of steps. That's counting the number of steps. So I leave off the end column usually. Okay? So if you want to do this in your notes, and this will be an example of what this is going to look like when we do it. So this, I just call this x and y. I usually don't put the sub in. But that's just x and y. Okay? Now, we're going to start with 0 and 1. So there's our initial condition. Again, I don't do this first column. So we're going to put our initial condition in the first row of our table. So x and y. So we're starting at 0, 1. Okay, now, the next thing we need to do, now remember, we've also calculated our step size here, right? We've calculated our step size. So that was 0.5. Now, that's going to come in here in a minute, but I would always have done that first. Okay, now, so there's our point. We've just plotted the point 0, 1. Okay, now, the next thing we're going to do is calculate our slope, just like we do with slope fields. So we're going to take our 0 and our 1, we're going to plug it into our differential equation. Well, of course, we can't plug in the 1, there's no y, so we plug in the 0, what do we get? We get a slope of 0, so we're going to put that column right there. So I would probably label this column y prime instead of dy dx, but that's up to you. And you might also write next to it that that's a slope. That's the slope, right? I think we get that, but that's a slope. Okay, now, here comes the most important column of all. The column that you're going to have, if you have trouble remembering anything, it's going to be this column right here. Okay? Because here's what we're trying to figure out. Here's what we're saying when we do Euler's method. We're saying, okay, I'm going to start here at 0, 1. I'm going to figure out the slope. Right? Now, I'm going to move over 0.5. Right? Remember that? We said that was our step size. So I'm going to start at 0. I know the slope is 0. So I'm going to move over 0.5. How much am I going to go up? Well, if the slope's 0, how much am I going to go up? 0, right? I'm not going to go up at all. But let's say the slope is 1. So if I go over 0.5, how much am I going to go up? 0.5, right? So the question is, how much so that's what we're trying to figure out. We know how far to go over. We know the run. We're trying to figure the rise. And so this column I call the rise. Okay? Now, right down here, they give you how to calculate that. If you take rise over run times the run, that gives you the rise. So in other words, we want to take our slope times our step size. Our run is our step size. That's going to give us our rise. So this column, so there's our step size, 0.5. So you probably have that written down already. Okay? So this column right here, I would call that delta y, or I would call that rise. That's the rise. Okay? Here's what I would also do there. Here's what I would also do there. I would write above there, I would write y prime times delta x. I would write y prime times delta x, because that's what we're doing. We're taking y prime times delta x. Okay? We're going to take our slope, our rise over run, times our run. That's going to give us our rise. Okay? Well, we know, of course, that's going to be 0 in this one, because if our slope is 0, we go over 0.5, we're going to go up 0. Now, here's another connection you can make between what we've been doing. Think about what we just talked about with our K2 and K1 formulas, right? Our K1, remember the K1 formula, or the K2 formula, where it was 0.75, remember that? And we said it assumes that the thing assumes it's going to be 0.75 curviness the whole time, but we know it's not. That's why it's off. Well, what's this doing? This is assuming that the graph is going to have a 0 slope for that whole step. Is it going to really have a slope of 0 that whole time? No, it has a slope of 0 here. We're going to assume it has a slope of 0 for that whole step. We know it's not, so we're going to be off a little bit. That's right. That's why this is an approximation. Okay, keep going. So the last column is our new y. I would make your last column, I would call that your new y. Because now you had your old y, which was 1, and then you have your rise. So how much are you going to go up? Well, we're going up 0 this time. So what's our new y? Our new y is 1. Okay, so we can go ahead and plot that. And then we go down to our next column. Now again, I wouldn't do this first column right here. We go down to our next row, I wouldn't do this column. So our next row is 0.5. Now for me, if I was doing this table, here's what I would have done to start. Since I knew my step size was 0.5, I would have went at my starting point 0, then I would have went 0.5, 1, 1.5, 2. You might do that right now. I know my step size is 0.5, so I'm going to go 0, 0.5, 1, 1.5, 2, because that's where we want to finish, right? Is it 2? Okay, so I would have done that so I know what's going on here. So my new y is 1, so I just carry that down to the next row. So now I'm at 0.51, which is right over there. Now what do I need to do? Repeat the process. I need to calculate my slope. So now I've moved over to here, and now I'm going to go, okay, now what's my slope now? Okay, so we're going to plug it in. What do we plug in? We plug in the x, 0.5, which is 2 times 0.5? 1. So our slope is 1. So now I'm over here, and now my slope is 1. So I'm going to go over 0.5 and go up what? Slope is 1. Over 0.5 up 0.5. Right? If the slope is 1, you go over 0.5 up 0.5. But here's how we'll calculate it right there. We're going to take, remember what I told you to write here? Take your slope times your run. So take your slope 1 times your run, your step size, 0.5. Take your slope times your step size. That gives you your run. So it's going to be 0.5. So we're going to go up 0.5. So my new y is 1.5. My old y was 1. My new y is 1.5. Okay, so I'm now where? I'm now at the point 1, 1.5. There it is right there. Okay, I'm at 1, 1.5. Okay? All right, now we do it again. We need our slope. So we're going to take our x, our 1, we're going to put it in there. 2 times 1 is 2. Okay, that's our slope. How do we get the next column? How do we get the rise? We take 2 times 0.5, right? Write it down. Write it down. Write it down, Mike. Right? Right there. Slope times step size. This column is slope times step size. So we take our slope, 2, times our step size, 0.5. And that is 1. That's our rise. That's our rise. If our slope is 2, that means if you go over 0.5, you're going to go up 1. Okay? And so what's your new y? 2.5. So our new y is 2.5. So we bring that down to the next row. So we're now at 1.5, 2.5. Okay? And there's what it would look like if we were graphing. Okay? And we got to go one more time. So we're going to calculate our slope. So we're going to take our x, plug it in. 1.5 times 2 is 3. We're going to take our slope times our step size. 3 times 0.5 is 1.5. That's our rise. We got our old y plus our new y, or excuse me, plus our rise. So we got our old y plus our rise gives us our new y of 4.0, and that is our final point. And so we just came up with y of 2 equals 4. Now what do we know y of 2 is supposed to be? Right? Y of 2 is supposed to be 5. Well, of course, it's off because we made those assumptions the whole time. What would make this be better? More steps. Yeah, smaller steps, right? Make delta x 0.1. What makes rectangles better? More of them, right? See all the connections here? See why we're doing this at this time? Because it's very much the same thing. Matter of fact, that's what calculus is all about. How do you make 2 points, a 2-point slope calculation get close to being a 1-point slope calculation? Get closer, right? The delta x is like the h. Get closer. I mean, if you had to summarize all of calculus in one concept, it's this right here. In all the major things that we do in calculus, it's all about better and better approximations, getting closer and closer and closer. to an answer. The idea of a limit. Right? That's the key. That's the key to all this. Okay, so we know this is what I already went through over there. Okay, we already know that the exact value is 5. Okay, and so this is called Euler's method. It gets more accurate as you go along. Okay, the TI Inspire has Euler's method built in. So everybody get your calculators out and let's do this. Now this is a couple years old, so a few of the menu options have changed just a little bit. But here's what we're going to do. So now, remember on the screen earlier I said we're going to do 10 steps? Okay? So we're going to do that in a minute. We're going to do 10 steps in a minute. First, we're going to go with the one that's on here. Okay? So we're going to do this differential equation right here. Okay? We're going to do this differential equation right here. Okay? So here's how we're going to put it into our calculator. So everybody go to your menu, go to your graph entry. Now I don't think differential equation is number 7 anymore. I think it's number 8. Okay? So we're going to go to our graph screen. So this is how we're going to do it on our calculator. We're going to trace on our calculator to get y of 2. Okay? So we're going to trace, go to differential equation, which I think is number 8. Now yours is up at the top, I think, instead of the bottom. Now we're going to change how we type this in just a little bit. Okay, do you see how, does everybody's come out and say y1 like this? Okay, everybody's look like this? Okay, now you have to type this in, but does it have a y1 right here? Graph entry as number 3. Number 3, and then a differential. Okay, now here's what I want you to change. Hang on here a second now. I want you to not put y1, because then we always forget. Because our differential equation is always given to us with y's. So because we can actually edit this, which you can't in the other graph modes, go in here and delete that 1 out of there. And just make that a y. And then just make these y's also. So all these that say y1s, just make those y's. Because it never fails that they give you a y1 here, and then you go in here and forget to put these as y1s. Okay? All right. Actually, if you had a differential equation that was p prime, you could actually make this a p in here, because the prime's right here. I don't know if you can see it. But that little mark right there is the prime. See? So you could put p in here, and then you can put p here too. All right. And then x, and the x has to be your input, not t. Right? So if you get a differential equation that got t's in it, when you put it in the calculator, you don't have a choice. You got to use x's. Okay, but we can't do the y. Okay, so anyway, let's type that in, and let's put our initial condition in there, 0 and 10. Okay? All right, so if you get that typed in, okay, let's see if you all get what they get here. Are you getting that right there? Now we're going to change our window here. So they're going to have us change the window. Okay? So let's go in our window settings. Let's go 0 to 250 and 0 to 150. 0 to 250, 0 to 150. And then it looks like that. And now we can trace. So try to trace. And I'm gonna move on here. Because the rest of this we don't need to worry about. All right, now hit your right arrow, Cody, and trace for us here. Oops, what happened? There you go. Hit trace. You still got that other F1 in there. But yeah, just go to menu, trace, graph trace, okay? And now hit your right arrow, okay? Now notice that's going by 0.1s. It's going by 0.1s here on his X. I'm guessing everybody else's is probably doing that. Okay, go ahead and hit your tab key. Go ahead and hit your tab key, everybody, to get back into there. Now he's still got his other equation in there. All right, an arrow up. See, that says D2, right? That's differential equation 2. So now here's his one. Okay, now see these 3 dots over here? This is important. This is important. So not only set the window, these three dots over here, so you need to kind of trace over to that. There you go, where it says edit parameters. So we need to be able to go over to those three dots, and you're going to get a screen to pop up here. What happened? Okay, click on that. Okay, so everybody see that? So it says a solution method Euler. Okay, hit the right arrow. If you hit the right arrow, there's another one that says Runge Kutta. Think of it this way. Euler's like left rectangles. Runge Kutta is like Simpson. It's better. So you get a better approximation, but it's more complex, and we don't want to get into it. Euler, we want to do Euler because that's what we're comparing to. So you want to make sure it says Euler. Okay, so keep it as Euler. And the rest of this we want to keep the same. The only thing we ever change in this, if we scroll down, we never change the plot start stuff, scroll down, keep going. The only thing we change is that plot step. That plot step is where that's our step size. So we were using 0.5 in the last problem, right? So that's where we would do 0.5. Okay, so why don't you go ahead and change it to 0.5 right now. It's probably, we're going to have to go back into it again anyway, it doesn't matter, but go ahead and hit enter. Okay, and now if we go back and trace, now let's go back and trace on this. And now start typing, or going to the right arrow, I mean. Notice how it's going by 0.5s now? See how it's going by 0.5s where before it was going by 0.1s? Because this is not the exact solution curve. This is just a whole bunch of points being plotted using Euler's method, like we just did in our table. Okay, so now let's delete that out of there. Everybody, let's hit tab. Let's delete that differential equation out of there, and let's put the one in we were just doing on our table. Okay, so let's delete that out of there, and let's do y prime. Okay, here's our y prime equals 2x. Remember the one we just had, that we just did the table for? We did y prime equals 2x. Okay, and our initial condition was what? 0, 1. So let's do 0, 1. Okay, and then let's go over to our step size. Let's go over to our three dots, and let's change that to 0.5. Now let's see if it is 0.5. I don't know if it'll still be 0.5. Yep, it is. Okay, so we change our step size. So that's something you always have to put in there. You have to put in your step size right there. Okay, now let's go ahead and hit enter. And I don't know, this window's probably not going to be good. What happened? Did you not hit enter or what? What? 2x. 0.5 should still be good. 0, 1. Hit enter. There you go. Okay, now let's go to our window. Let's set our window this time. And I would give you the window measurements probably or they'd be fairly obvious. Or else just a standard window. Let's go 0 to 4. Let's go -1 to say 20. Okay. And there, see now we still have that other function graph. It'd been good if we did, before you're doing differential equation graphs, delete out any function graphs you have, but that's fine. So we just care about those dots. Those dots are those Euler points that we did earlier. So go ahead and trace. Go ahead and trace now. Okay, everybody tracing. So now type in a 0. Type in a 0 first. Okay. Oh, you're on that other graph. Hit your up arrow. This is why it gets confusing. Hit your up arrow. There you go. Now hit 0. Okay, so now we're at 0, 1. Remember that was our first point? Now hit your right arrow. And then 0.51. Remember that was our second point when we did the table. Now hit your right arrow again. Now we get Now we get 1, 1.5. What are you doing?
Nothing, it's just every time I click right, it's doing.
You sure you're not hitting the home screen?
Oh, look.
Okay, so up there. Now you're, okay, 1, 1.5, now back up. So he's at 1.5, 1.5, 2.5, remember that was a point we had, and then finally the last point was 2, 4, 2, 4, right? Those were our points. Now, we want to do it with 10 steps. So remember my directions here? So 10 steps, that's an automatic use your calculator. 10 steps is an automatic use your calculator. So this is table. single digit steps, we have to write it out. 10 steps, double digits, automatic, you use our calculator. So what do you have to calculate though first? Step size. So what's our step size going to be for 10 steps if we're going from 0 to 2? Which would be 0.2, right? 1/5, 0.2, right? That's our step size, 0.2. So let's go back to our calculator. So this is how you would use your calculator. So you would tab, you would go up there to the 3 dots. We're going to change our step size to 0.2. Hit enter. We're going to trace. And you could go right to 2 if you want, or you could start back at 0, whatever. But all we care about really is what's y of 2. And look at that, 4.6, it's better. It's not exact. The right answer is 5. But it's better. It's better. We're getting closer. Okay? So 4.6. So all you would write down, if this was the quiz, all you would write down is y of 2 equals 4.6, and that's all you'd have to write. Just like you're doing an M50, you would just write down the answer, right? Y of 2 is 4.6. So it's very much the same kind of thing. We're doing an approximation. We do 0.1. If we do 20 steps, 50 steps, it would be getting better. It'd be getting better, right? Smaller step size, we'd be getting a better approximation. Okay, I'm not going to go through this next one with you, but this would have been just one. This is just another one of doing the table. Okay, this is what my table would look like. I always make myself a little note there of what I want the table to look like. You're going to have to do a couple of different tables on the homework, okay? But there's your initial condition. You're trying to go to 5. So if I told you I wanted you to do 4 steps on this one, it would be 5 minus 0 divided by 4, right? 1.25 would be your step size. So what I would do is I'd come over here. We're starting at 0, 1.25, 2.5, 3.75, and then 5. And there would be my 4 steps, right? What's that? That should have been in X. Just like, yes, that should have been in X. Okay? All right. Now, there might be, I'm not sure if there is on the homework, but this is just a little review of verify. Remember how we used to verify something was a solution, right? We verified that this is a solution, so we would do the derivative of this, and we put that over here. And then we put this is our y, we put that in there, we work it out, we show that the 2 sides are the same, the old T-chart thing. So there might be a little bit of that. But we'll have tomorrow some time to work now and ask some questions if you need to. Okay, so here's your homework. On that 6-3 line, I took a couple off. I took off number 1, and I took off number 2. Number 6 is just kind of asking you some questions about a scenario that you got to kind of think about. 8 and 11 and 15, you have to make a table. Now, the only reason I wrote that on there, I just wanted you to see, remember, single-digit steps, you do a table. So those problems have multiple parts to them. So I think like number 11, for example, has one you have to do 4 steps, so you have to do a table. And then it has 10 steps, so you can just do your calculator. I think 13 has 20 and 40 steps, so you just do your calculator on those. I think 15 has another one that's 4 steps, and then it's like 10 steps. So you do one with a table, one with your calculator. So when I come around tomorrow, I'm going to come around and look for your tables. I want to see you have to, for sure you'll have to do that on the quiz. You have to do both those things. You have to be able to do a table, and then you have to be able to do more steps, or on your calculator too. All right, that's pretty much it. That'll be on the quiz on Thursday. We'll use tomorrow to kind of review that stuff. Okay?
You want your doohickeys?
Yeah.
They are.
Thank you.
What?
Nothing.
No, I'm serious. Every time I click over it, go home.
No, I believe you.
When you came over.
That was kind of weird, yeah.